Welcome back to the Explainer. Today, we're tackling something that is literally keeping enterprise data teams up at night, building the private enterprise RAG stack. If you're looking to construct the ultimate, fully private AI pipeline based on the absolute latest industry data, you're in the exact right place.
Think about it for a second. How on earth do you build enterprise-grade AI without shipping your most sensitive data off to some external API? It's a massive roadblock, right? Finance, healthcare, legal teams, they all have incredibly strict data residency rules. They want the magic of AI for sure, but they absolutely cannot leak their proprietary documents to the cloud. It's a huge challenge. Okay, let's dive right into this blueprint. First up, we'll look at the privacy mandate, then Command A, our generator. After that, we'll fix search with re-rankers, benchmark the absolute best ones out there, and finally, we'll look at the ultimate RAG ceiling. Let's get moving.
All right, part one, the privacy mandate and localizing enterprise AI.
So we've got to start with why this shift is even happening. Finance and healthcare teams, for example, simply cannot send highly sensitive documents to external APIs. No way. The regulatory and security risks, off the charts. So this strict data residency mandate really forces enterprises to self-host the entire brain of their AI stack right on their own local GPU infrastructure. We're talking about bringing the intelligence inside the corporate fortress, rather than sending your data out.
Moving right along to part two, Command A, our generator.
For the generation layer of our stack, we're looking at Cohere's flagship open-weight model, Command A. And honestly, the sheer scale here is wild. 111 billion parameters and a massive 256,000 token context window. To put that 256K into perspective, that means a self-hosted system can process full, incredibly dense legal contracts or massive research corpora, all in one go. You don't have to awkwardly chunk them up into smaller pieces anymore. It is an absolute game changer for preserving the full context of a document. But look, it isn't just about size, right? It's about precision. Command A scores an 80.7 on the Berkeley function calling leaderboard. It delivers highly reliable structured output for tool calls. It's totally optimized for multi-hop agentic tasks, and you can deploy it on infrastructure like Spheron H200 or A100 GPU nodes. That function calling score is absolutely vital because it means the tool calling reliability outshines older models. It makes this the perfect foundation for chaining those really complex agentic workflows entirely on your own local hardware.
Okay, on to part three, fixing search with re-rankers.
Now, what's really interesting about this is, well, you have your generator, but how does it reliably find the right data in your corporate vault? You absolutely need a high-precision retrieval filter. So let's get our terms straight so we're on the same page. A cross-encoder, which is also known as a re-ranker, evaluates a query and a candidate document together. It attends to both texts jointly to catch those nuanced relationships that independent encoding just flat out misses. It's essentially looking at the query and the document at the exact same time, acting as a high-precision quality control checkpoint before the AI even sees the data. To really wrap our heads around this, let's compare the two steps of modern search. First, you've got your dense retriever, or bi-encoder. This encodes queries and documents independently. It is super fast, highly scalable for nearest neighbor search, but it totally misses nuanced relevance. Then, step two is your re-ranker, the cross-encoder. This processes the query and document together as a single input. You get deep contextual accuracy, but yeah, at the cost of speed. This structurally explains why a two-step process is a must-have. You need that fast bi-encoder to instantly grab the top 100 documents out of millions, and then that slower, highly precise cross-encoder steps in to scrutinize that top 100 and find the absolute best fit. A fantastic example of this layer in action is Cohere Rerank 4, which actually gives you two specialized variants for Oracle Cloud infrastructure. You've got Rerank 4 Pro, which is optimized for high precision and complex tasks, and then you have Rerank 4 Fast, optimized for low latency, high throughput workloads. This shows exactly how enterprises can make strategic trade-offs between ultimate precision and blazing speed when they're deploying their infrastructure. Rerank 4 also packs some standout features. We're talking a 32,000 token context window, self-learning support without needing annotated data, by the way, plus it's multilingual across over 100 languages, and remarkably, it even supports semi-structured JSON and tabular data. That 32K context window, that is perfect for dense technical manuals or massive enterprise reports, letting the re-rankers see the whole picture before making a relevance judgment.
All right, part four, benchmarking the best re-rankers. So it is time to look at some hard data. We pulled from a benchmark of 145,000 real-world Amazon reviews, focusing on hit-at-one accuracy, meaning did the model put the exact right document in the absolute #1 spot? The baseline, with no re-ranker at all, sits at 62.67. Now, the massive Qwen 3 4 billion parameter model, that hits 77.67. But wait, look at the tiny GTE_modern BERT 149 million parameter model. It scores an 83. And this brilliantly illustrates a huge surprise in the data. A massive 4 billion parameter model is literally beaten outright by a tiny 149 million parameter model. Crazy, right?
The benchmark really spells it out perfectly here. The 14 million parameter GTE modern BERT matched the massive 1.2 billion parameter Nemotron 1B with an identical 83% hit-at-one accuracy. Basically, in the specific world of re-rankers, massive model size just isn't everything. The smaller, highly efficient modern BERT architecture delivers absolute top-tier accuracy, but with a mere fraction of the memory footprint.
But, what if speed is your absolute primary concern? Well, the benchmark found that Gina_Reranker_V3 offers the best speed-to-accuracy trade-off. It hits a really impressive 81.33% accuracy with a blazing fast 188 millisecond latency. For latency-sensitive enterprise applications that are crunching thousands of requests per second, that sub-200 millisecond speed is exactly what you want.
We do have to note a pretty crucial warning from the benchmark, though. A re-ranker is not automatically beneficial just because you dropped one into your pipeline. Case in point, the 70 million parameter MXBy Rerank XMall only improved the baseline by a negligible 2%. Choosing the wrong, underpowered model can literally just add latency to your system without delivering any meaningful accuracy gain. You absolutely 100% must test before you deploy.
And that brings us to our final section, the ultimate RAG ceiling. Okay, so we've built the local generator, we've tuned the search precision, but now we really need to analyze the absolute structural limits of this whole pipeline. So the crucial point is this: the retriever sets the ceiling. Think about it. No matter how incredible your re-ranker is, even if you use the absolute best cross-encoder on the planet, it cannot rank a document that the initial dense search completely missed. The benchmark data totally proved this ceiling exists. All the top re-rankers hit a wall at about 88% hit-at-10 accuracy. Why? Because the initial E5-based dense retriever completely failed to place the correct document in the top 100 candidates to begin with. To break past this 88% accuracy ceiling, you can't just keep upgrading the re-ranker. You have to go back and upgrade your initial dense retriever. Which leaves us with this final thought for today's explainer. If the retriever sets your ceiling and the re-ranker defines your ultimate precision, what is the true bottleneck in your enterprise AI stack today? I highly recommend taking a hard look at your own pipelines based on this blueprint. Thanks so much for joining me, and we'll see you next time as we keep decoding the cutting edge of tech.